Hi guys, and welcome to our Wadix Technologies YouTube channel. Wadix Technologies is a company specialized on embedded systems training and online coursing. We offer a big variety of free online courses specialized on embedded systems technologies. All of this is within our YouTube channel. We provide as well blogs, articles, advanced online courses, and one-to-one training services specialized on embedded systems technologies within our website www.wadixtech.com. So don't forget to hit the subscribe button of our YouTube channel, as well as checking out the different services we offer within our website wadixtech.com. Hi guys, and welcome to today's course. In today's course, we're gonna go through the Ninja build tool system. First of all, we'll see the added value introduced by the Ninja build tool, as well as the main features supported by Ninja. We'll go through concrete benchmarking and comparison between Ninja and Make build tools. We're gonna see as well the main command line options supported by Ninja, as well as the supported generic syntax. And finally, we're gonna conclude this course by a Ninja-based project where we're gonna write our first Ninja-based build system. So welcome to this course. Similar to the different build tools like Make or build system generators like cmake, the main idea behind Ninja is to automate the flow of compilation of our embedded system based project. So instead of compiling, pre-processing, and linking the different sources one by one, we're gonna automate the whole flow by using our Ninja as build system to generate the final binary. Hence, instead of providing the sources one by one for pre-processing, then compiling those pre-processed sources to object files, and then linking all those object files one by one to generate the final binary, which will be loaded into our hardware device, the Ninja allow writing our complete build system to automate this whole flow. So instead of processing the different sources one by one, we can just provide the whole project to our Ninja based build system, and then the build system will automate the flow of compilation and generation of our final binary. Ninja is considered as a fast build tool, at least compared to Make. Ninja expects a pre-computed dependencies graph to be able to execute or focus on executing only the different Ninja rules. This is totally different from Make approach. When executing our makefile, the resolution of the different Make dependency rules will be done during the build time. And hence, the build time using Make will be extended and bigger compared to Ninja. Ninja does support incremental build. This means Ninja will be able to detect any modification for the concerned files and hence trigger the build only of those modified files, not the whole project. And this is of course similar to Make. However, what is different compared to Make is that Ninja has the option to detect extra dependencies. In fact, with Make, we'll need to go through the different files involved within the different Make rules, and then check the modifications that occurred on those files, one by one. However, in Ninja, we'll have all the concerned files stored within a single Ninja depth source file. And hence, Ninja during the build will go to this Ninja_depth file to check if one of those files has a changed or modified timestamp. Ninja does support parallel build. This is similar to make. And hence, we can execute the different Ninja rules in different threads or processes. Similar to make, Ninja does support inclusion. Means we can split our project in multiple Ninja files, and then we can include all those sub-Ninja files within the main Ninja build file. However, Ninja does not support any built-in functions like make. Also, Ninja does not support recursive execution like makefile. If we will try to summarize the main differences between Ninja build tool and make build tool, we'll see that the main features and ideas behind Ninja are around the idea to make Ninja a faster build tool compared to make. So first of all, Ninja expects a pre-computed dependency graph to speed up overall build time. On makefile, we'll need to parse the different makefile rules to create this dependency graph. And this parsing and the creation of the dependency graph is done on each and every run. To eliminate basically this extra stage of creating this dependency graph, Ninja will expect that we list all those dependencies within the main Ninja build file. And hence, Ninja will be able to start right away the execution of the different Ninja rules without creating this dependency graph. Ninja does not support recursion. On makefile, we can execute or trigger the execution of a makefile within another one. Although this is a strong feature, but it is known by slowing down overall build time. To eliminate this extra overhead, Ninja does not support natively this recursion feature. We know that on makefile, we have the support of if statement conditions, loops, some built-in functions. Although those features offer certain flexibilities to the user, but they are slowing overall build time. In fact, on makefile, the make will need to parse those conditions, loops, and built-in functions to be able to evaluate them. And this parsing will add extra overhead to our build time. To eliminate this parsing time, Ninja does not support all those features. Ninja has efficient timestamp checking and detection compared to make. On make, we'll need to parse the different makefile rules and verify or detect the different files needed by those rules. And hence, make will need to check the timestamp of those dependency files one by one to see which one has modified or updated timestamp. Ninja is quite different. Here, all the files or sources that our rules need them will be stored within this Ninja deps file. So we are centralizing the information about the file that our project needs them within a single one. And hence, to get the list of the file to check their timestamp, Ninja will go right away to this Ninja deps file. Then we'll check basically the timestamp of the different files listed within this Ninja deps file. So instead of evaluating the different rules to get the list of those files, the Ninja will need just to read out this Ninja deps file to get this list. Ninja, of course, does support immediate parallelism compared to make. In fact, Ninja can throw the execution of each of the different rules on separate process or thread. However, on make, we cannot guarantee this, especially with the support of recursion. There we need to evaluate basically this recursion, and this will block basically the spreading or splitting of the different rules on separate thread and processes. However, in Ninja, as we don't have the support of recursion or any extra bottleneck or overhead to slow down or stop the splitting of the different rules on separate process and thread, with Ninja we can start right away executing on parallel the different rules. Ninja does support incremental build. Means Ninja will be able to detect the updated or modified files to be rebuilt. So instead of rebuilding the whole project, we'll recompile and build only the modified or updated files. This feature is supported as well by make. However, the main difference is that on make, we'll need to parse the whole make files. Then we parse the different makefile rules to create this list of the files that we need to check. On Ninja, this is quite different. This list of the files to be checked will be centralized within this ninja_deps. So instead of parsing the Ninja build file to create the list of the files to be checked, Ninja will read only a single file, and it will be able to get the full list out of this file. And then it will check the timestamp of those files one by one. This will eliminate this overhead of getting and creating basically this list of files out of the different rules. Instead of that, we'll have the full list of the files to be checked within this ninja_deps. How to check if a file is modified or not? Similar to make, the Ninja will check the timestamp of the concerned file. If it is updated, then of course the file will be recompiled and built again. If not, then it will not be touched. Hence, instead of rebuilding the whole project, we'll rebuild only the concerned or modified file. Ninja does support parallelism. This is quite similar to make. Means we'll be able to execute the different rules, each one within a separate thread context. However, the main difference is that on make, we'll need first of all to create the dependency graph before we'll be able to assign or create those threads. This will add, of course, extra overhead. Then on make, we have the support of the recursion. Means even if we are able to assign different threads to our makefile rules, the execution of another makefile will stop basically this process of threads executions. And we need to evaluate again the different rules within this makefile. And then we may or not create another set of threads for those sub-makefiles rules. Hence, we may end up by a single thread executing the different recursive makefile rules. This is, of course, will break down the parallelism concept. On Ninja, we'll have a pre-computed dependency graph. So Ninja already is aware of the different rules that will be executed, and it doesn't need to evaluate those rules to be able to create the list of the dependencies. Hence, it will be able, first of all, to start right away executing the different rules, each one within a separate thread. Second thing, we'll have a single process to execute our Ninja tool. And out of this process, we'll be able to create a set of threads. Each one will execute a separate Ninja rule. This whole flow will start right away. So there is no overhead of parsing the Ninja build file to be aware of the dependencies between the different Ninja rules. Everything is listed right away and in clear way basically in the main Ninja build file. This of course will allow using the full capabilities of our hardware in terms of CPU cores to make the execution of our build flow in as parallel as possible. Finally, there is no blocking waiting for task to finish. Hence, we are speaking up about like kind of real parallelism between those different threads. Hence, one thread will not wait for the other to finish. No, this will have its own isolated context compared to this thread, compared to this one and this one. This allows, of course, speeding overall build flow. Ninja does support inclusion. Means we can break down our Ninja-based build system into .ninja files, and then we can include all those .ninja files within the main Ninja build file. And this one will be, of course, our entry point to build this whole project in respect to Ninja build tool. This is quite similar to what we have with makefiles. There, we can break down our makefile based project into .mk files, and then we can include all those .mk files within the main makefile. And this one will be the entry point to build our project using make command. Here, to add those .ninja file within the main Ninja build file, we'll need to invoke this subninja command or syntax. So we invoke the syntax with the path to our Ninja build file. This is a block diagram to illustrate how the Ninja build tool will be able on every run to build only the modified or updated files. And this is, of course, what is called the support of incremental build. So during the first run, Ninja will create what is called .ninja deps file. This one will embed the list of the files and sources that are needed by the different Ninja rules to be able to compile our project. So instead of evaluating the different rules to get the list of the files, actually, and because we have a pre-computed dependency graph, Ninja knows already by default the different rules and the different files needed by those rules. And hence, for the first run, it will be able to create right away this .ninja deps to contain the list of the sources needed by our project. Then, for the second, third, and so on runs, it will read out first of all this file on every run, then get the list of the files to be checked, and then it will verify the timestamp of each of those files. If it found out that the timestamp of one of those files has been updated, then it will rebuild only the concerned and updated file, not overall project. With that, first of all, we are minimizing the overhead of parsing the different Ninja rules to create on every run the list of the files. Then we'll be able on efficient way to detect the modification and updates that has occurred within one of those sources. This is a summary of the different command line options supported by the Ninja build tool. We have, for example, this -- version to get the version of the current Ninja build tool in use. -- verbose, this to show up the progress of the different commands executed by our Ninja build tool within the current console session. -- quiet, this is to minimize overall output coming from the Ninja build tool. -f, This is needed if we want to specify a different .ninja file rather than the default one. This means that when executing our ninja command, it will try to find out on our top level directory this builder.ninja file. This is the entry point for the ninja command to build our project. If we have a different file name or different location for this entry point, then we need to override the default one by using this option. -G, this is used for parallelism to specify how many jobs will be used to run the different ninja rules. -K, this is to specify on which end jobs we should fail. Means we should keep going basically the execution of the different jobs until we reach end jobs fails. Example, if we have the support of 8 jobs and then we specify -K1, it means if the first job fails, then overall progress or execution will fail. There is one important option which we need to specify here as well, is this -T. This -T by itself embed another list of options and commands that we're going to specify later on, and needed overall to manipulate the execution or the build flow of our project, like cleaning up our project and so on. Beside the standard list of command line options supported by Ninja, we'll have another subset of commands allowing inspecting the current Ninja build system itself. This list of commands is known by Subtools. To invoke one of the Subtools command, we need to specify the -T option, then follow it by one of those Subtools command. With one of those Subtools commands, we can inspect the current dependency graph and even browse it using the browse command. We can even output this dependency graph. We can get the full list of the rules supported by our current Ninja build system. We can clean up the build directory by invoking the Subtools clean command. Hence, we don't need to create a dedicated clean Ninja rule to clean up the build directory. We can rely on the default Subtools clean command. We can display and show the full list of dependencies stored within our deps log file. So as you can see, guys, this list of Subtools command is very useful actually to inspect and help you basically to recognize the main issues that can occur within your current Ninja based build system. In terms of syntax, Ninja does support variables. This is quite similar to what we have on makefile as well. To create your variable, you need to specify the name of the variable, then use the equal mark to initialize your created Ninja variable by certain value. Here I have created the cc variable, which will hold the compiler name to be used to compile our project. I have created another variable cflags, then initialized this variable using the equal mark with a set of compiler flags to be inputted later on to our compiler. I used the Ninja variable syntax to create a command to be executed to compile our project. So this command variable has been initialized with the cc variable name, but this time the cc variable name will be expanded, means it will be replaced by its component here. So you can see this as arm-none-eabi-gcc, not cc. And to expand any Ninja variable, you will need to use the $mark. Then I have expanded the list of the compiler flags to be inputted to our compiler. Then of course I had to specify the input files and the final output binary. So this is the list of the input files to be expanded using this $mark. And finally, this is the output binary to be expanded as well using the $mark. So here I have the full list needed basically to compile our project. And this list has been used to initialize our command variable. Then later on, we can invoke this ninja variable command to compile our project, as you can see. Similar to any other kind of build tools, Ninja does support rules. To create a Ninja rule, we need first of all to use the Ninja keyword rule, followed by the name of the Ninja rule to be assigned. To initialize the body of the rule, which will be executed whenever we invoke this Ninja rule, we need to use the Ninja built-in variable command. We can link and assign certain description to our Ninja rule using this Ninja built-in variable description. Now, those two lines are must to have for any Ninja-based rule. Nevertheless, we can have certain optional fields to be specified for any Ninja-based rule. We'll have the dep file, deps, and pool built-in Ninja variables to be used within our Ninja rule. The dep file is used to specify the dependency file where we are storing the full list of the sources needed to be recompiled to create our output binary. This is more a GCC style where we are storing all those dependency files within a single .d file. We can specify to our Ninja how we can read and dump this .d file using this deps built-in variable. Here we are specifying the command or the tool needed to properly read this .d file. And finally, we can limit the parallelism behavior or concept of our Ninja by using this built-in variable pool. So this pool will consist of specifying the list of the jobs needed basically to create the different threads and process to execute our rules. However, we can limit this number by specifying this built-in variable, and hence Ninja cannot exceed basically the number specified within this variable. Now to execute our Ninja rule, we will need to create what is called Ninja build statement. To create a Ninja build statement, we need to specify the keyword build, followed by the list of the explicit outputs expected as outcome of the execution of our Ninja rule. Beside the explicit outputs, we can specify another set of implicit outputs, which are kind of side effect files coming out of the execution of our Ninja rule. Those explicit outputs are must to have, but those implicit one, it depends basically if we need them later on or not. To initialize our build statement, we need of course to invoke our Ninja rule, followed by the list of explicit inputs parameters that our Ninja rule depend on them. So those are kind of explicit dependencies. So whenever they are changing or getting modified, we need to re-execute our Ninja rule. Besides those explicit inputs, we can specify another set of implicit dependencies to our Ninja rule. Similar to those, if one of those implicit dependencies has been modified, then we need to re-execute our Ninja rule. And finally, we can specify what is called order-only deps. This is another set of dependencies to our ninja rule. However, this time, if those order only dependencies has been modified or changed, then we don't need to re-execute our ninja rule. This is an example basically on how we are creating this ninja build statement to invoke our ninja rule. As you can see, we need to specify the build keyword, the output expected out of the execution of our ninja rule. Then this must be initialized with the invocation of the ninja rule, followed by the list of the explicit dependencies to be able to build this ninja rule. Whenever this is changing, then we need to rebuild our project and re-execute the ninja rule. This is another line to specify the full list of inputs and outputs expected from our build statement. Again, this is the build keyword, this is the explicit list of outputs, and this is the implicit list of outputs. Here we are invoking basically our ninja rule that has been created in earlier stage. Those are the explicit input dependencies. Hence, whenever this one is changing, we need to re-execute this ninja rule. This is another implicit list of dependencies. And here we are specifying this tool which is needed to execute properly our ninja rule. Again, if this is getting changed, then we need to re-execute our ninja rule. And finally, we have this order only dependencies, and here we am specifying the output directory. So this guy, it must exist, but whenever this is getting changed, means or getting removed or renamed, then we are not rebuilding basically our ninja rule again. To build your ninja project, you will need to invoke the ninja command to parse the ninja build file and locate the default build target. The default build target is just build statement that will be marked with this default keyword. Hence, whenever we are invoking the ninja command within our top level directory, it will parse the ninja build file to recognize this default keyword, and then will invoke par consequence the corresponding ninja build statement. So the ninja command will look for the default target, and then this will be evaluated, as you can see, to execute the corresponding build statement that has been associated with our default target. The ninja build tool does support special built-in variables. Here, with this $in, we can expand the list of the input files to be specified within our ninja rule. Similar to the input files, we can expand the list of the expected output files within our ninja rule. So whenever we are creating our ninja rule, instead of hard-coding the list of the input files and expected output files coming in and out of our ninja rule, we can just utilize those built-in variables that will be expanded later on to the full list of the input files and expected output files. So whenever we are invoking and executing the build statement that will execute and call and return our ninja rule, the default input files specified to the build statement, which will be passed later on to our ninja rule, can be referred using this $in variable within our ninja rule. And the expected list of output files coming out of the execution of our build statement, which are in return coming out of the execution of the ninja rule, can be referred within this rule using this $out variable. By default, the list of the input files and expected output files are space separated. If we want them to be lines separated, then we can utilize those special built-in variables $in_newline and $out_newline. Our project will be a Ninja build system based project, and this project is dedicated for embedded systems, and to be more precise, we'll be targeting an ARM Cortex-M based microprocessors platforms. To be able to compile the list of the C sources for this ARM Cortex-M microprocessor, we'll need a compiler and toolchain. The compiler to be used will be the arm-none-eabi-gcc compiler. This is the GNU GCC compiler version for ARM Cortex-M microprocessors. Besides the toolchain, we'll need, of course, the Ninja build tool itself. Apart from those two main components, we don't need, in general, external tools or applications to be used within our Ninja build file. The main idea behind Ninja is to make it as fast as possible. Hence, we are trying to eliminate any kind of pre-processing stages whenever we are invoking Ninja build command. Therefore, we want to avoid and prevent the utilization of any external applications or tools that can be invoked during this pre-processing stage. Now the toolchain and the Ninja build tool itself can be found under our tools GitHub repository, and this is the link. Our ARM Cortex-M based project, which will be as well a Ninja build system based one, will be located under our GitHub repository. And this is the link to our GitHub repository where this project will be located. Anyhow, the different links will be provided as part of our YouTube description. And there you're gonna find as well the slides and the source code of our projects. So guys, this is the top level overview about our ARM Cortex-M based project. As you can see, this is a minimal project to demonstrate how we can use Ninja to build an embedded system based project. Here I'm gonna have the main.c and the startup.s to boot our device. Here I will have the list of the headers, and finally I will have the linker script to link the different objects and generate the final binary. First of all, I will start by creating a dedicated Ninja file to encapsulate the list of the toolchain applications to be used to compile and link and post-process the final image. I can call it arm-toolchain.ninja. Here I'm specifying basically that this is dedicated for ARM-based platform. First of all, I will start by creating a Ninja variable to hold the absolute path to our ARM-GCC toolchain. Then bin. Then I will need to specify the list of the toolchain applications to be used to compile, link and post-process the embedded based image. So I'll need one for the compiler, one for the assembler, one for the linker, one for the object copy. This is needed actually to generate the final binary, and one for the object dump. The compiler, of course, will be the arm-none-eabi-gcc. So I need to expand the content of this Ninja variable. This can be done via this $, then the name of the application. The same application will be used as well as assembler and linker. For object copy, I'm gonna use the object copy application. And for the object dump, which will be needed to generate the disassembly out of our ELF image, I'm gonna use the object dump. So this one will be used to convert the ELF to a binary file, which will be loaded to our target device, and this one will be used to generate the disassembly to inspect the assembly level of our image. I will need now to create another Ninja variable to hold the base flags to be provided later on as input to our compiler, assembler, and linker. And those base flags needed to specify the processor name, which will be the Cortex-M3, as well as the instructions encoding mode, which will be in our case the thumb encoding mode. So this is our base flags, and this will be stored within this Ninja variable named CPU_flags. Now to specify the CPU name to GCC, we need to utilize this option -mCPU, then follow it by the processor name, Cortex-M3. Now for the instruction encoding mode, we can utilize and invoke this option -mthumb. Now for the compiler, we'll need to create another Ninja variable to hold the different options to be able to compile the different C sources. For this, I will create the cflag Ninja variable. Then I need to expand the base flags, which is gonna be the CPU flags. This can be done via this $, then CPU flags. Then I will need to add on top the other compiler flags, like the optimization level, throwing all warnings. Then I can specify the list of the include directories. For that, I can add this Ninja variable as well. So here I will have another external Ninja variable outside the scope of this file, and then it will be expanded so that we are able to provide the paths to the different directories that contains the different headers. So this $enc_dir will be extended or expanded later on with the current value of this Ninja variable. And then I want to create another GCC style based dependency file so that I list all the headers dependency lists. This can be done via this mmd and mf. And of course, I need to specify this dependency file itself. So this file is expected to have the list of the headers. If one of those headers get modified or updated, then the whole project will be recompiled. And this is a GCC way basically to tell the build system that those are the list of the headers that we need to build our project whenever one of those headers get updated. Similar to the C compiler flags, I will need another set of options of flags for our assembler. Here I'm going to create another Ninja variable, and this one will be initialized first of all with the base flags, and this one gonna be the CPU flags, then followed by one or more assembler flags or options. Now the assembler and the assembler options will be needed later on to compile our startup.s file. Finally, we'll need now to create the list of the options and flags to be passed later on to our linking stage, so that we generate out of the different objects the final image. I'll create another Ninja variable. Here I will keep the same style of naming those variables. So this will be the LD flags. Again, I need to specify the base flags, which are the CPU flags. Then I need to specify linker specific options, like the path to our linker script. This can be done via this -t option. I will have another Ninja variable to hold the path to our linker script. Then the name of the linker script.ld. So this variable can be defined outside the scope of this Ninja file, and here it will be expanded to the path to our linker script. Then no start files, and then I will have another backend based linker option, which is needed to minimize the size of the final output binary, and this will be the -- garbage collection sections. And we are ready. Now we're gonna include basically this arm-toolchain.ninja file within the main Ninja build file. We're gonna need now to create our build.ninja file, which will be the main entry point to build our project using Ninja build tool. So whenever we are invoking Ninja, the first file it looks for it will be the build.ninja. Here, the first thing to be done is to create what is called build tree. It means basically the list of the directories where we are having our sources, headers, and linker script. So I will call it like source tier. So this is basically a Ninja variable that will hold the path to the source directory. Now the source directory is here. So this is the name of the directory. Then we need to redo the same for the include directory. Then linker directory. And finally, we're going to specify the expected name for our build directory. There we'll have basically the outcome of the compilation of different sources. After that, we'll need to include the arm-toolchain.ninja file that we have created and which define already the different toolchain applications to be used to compile and link our embedded system based application. So arm-toolchain.ninja. Now once done, we're gonna create the list of the expected outcome applications coming from the compilation of our project. First of all, we're gonna have the bin. This will be the firmware.bin, and of course we need to specify the location of this firmware. So it will be under build directory, and as you can see, I will use $ here to expand the ninja variable here. Then I will have the elf, or executable and linkable file. This is the binary with the debug symbols. And finally, I will have the map file. And then we are done in terms of expected applications and results out of the compilation and the build of our project. We're gonna need now to create the list of the ninja rules to be able to compile the different sources and generate the object files out of the sources. Then finally link those object files to generate those output binaries. So this section will be dedicated for the different ninja rules. Now the first rule to be created is the one to compile the different sources. We will need, of course, to provide the command to be executed to compile those sources. The command consists of invoking our compiler. So this ninja variable has been defined here, and it will hold basically the path to our arm-gcc compiler. Then we specify the list of the compiler flags or options. This is again another ninja variable that has been defined here. I will add another compiler option, which is -c. This is to say that we want to compile the source, not to link it. Hence, we are preventing the toolchain from compiling and linking each object separately, which will end up by having many images. The idea is just to compile all sources, then we do a single linking. Then we need to provide a built-in variable, which is this in. This is stand for the list of the input files and parameters to be provided later on whenever we invoke this rule. Then finally $out. This is another ninja built-in variable, and it will stand basically for the expected output object file. So this is again to be provided later on whenever we are invoking this ninja rule, and it will be expanded later on to the real, let's say, expected output object file. Now, as a mandatory field, we need to provide the description. Here I can state cc then out. Now this is the refer of compiling and generating as expected file this object file. There are two optional fields I will add here. Is this dep file. This is a GCC style based dependency file, and it is standing for a file that will contain the list of the headers, and whenever basically those headers get updated, then this ninja rule will get executed again. So the ninja will keep an eye on this file, and whenever there is an update within this file, then the ninja rule must re-execute this ninja rule again. And the application that will update this dependency file will be GCC. So far so good. Then we need to create another role for the assembler, another role for the linking, and finally another role for the object copy. This is needed to create the binary. Now again, as a mandatory field, we need to provide the command. So again, this will be the awesome flags, then -c to compile, not to link. Then this is to be evaluated the list of the input files to be provided with this ninja rule, and finally our output. As a description, we can state as and then out. Now for linking, will be something similar here, but here I will invoke the linker, then linker flags. I will add another linker flag which is used to generate the map file. So minus map, and here I will invoke the map. So if you remember, this is a Ninja variable that will hold the name of the expected map file. Now the outcome will be the final binary. So this is to be given by the build statement whenever this linker will get invoked. However, the input objects will need to be provided in this position. And again, LD, and we are done. And finally, for the object, it's quite similar here. We need to provide the command to be executed and the description. Now, the command should be the opt copy. Description can be this one. Then this is the flag needed by the object copy to generate the .bin file out of the .elf. And this is the output. This is to be provided later on by the build statement that will invoke the object copy, and this should be basically our .bin file. And this in1 should be later on the .elf. And we are done. So this is an overview about the different rules needed by our Ninja to be able to compile the different sources. Now we'll need to create the build statement that will invoke those rules. We'll need now to create the list of the build statement to be able to invoke the different Ninja rules which are needed later on to compile the sources and generate the outcome binaries. So this section will be used for the different build statement. Now the first build statement will be the one to compile our main.c file. The expected outcome will be the object file out of the main. This will be located under build directory, then it will be main.o. To compile the main.c, we need to invoke the Ninja rule to compile the sources. Then we provide the input source to be compiled. So this is under source directory, then main.c. Similar to this, we'll need to compile our startup code, but this one is .s. For that, we need to invoke the assembler, not the compiler, and the expected outcome will be, of course, under build directory. Now, after compiling, we'll need, of course, to link. So we need to create build statement to invoke the linker here. Now the outcome result will be, of course, under build directory, and it will be the .elf. Here we have already created a Ninja variable basically to hold the full path as well as the name of the .elf. So we can just expand it here. We need to invoke the linker. Now the input will be, first of all, this one, the main.o. Then we need, of course, the startup object. And then we'll create kind of implicit dependency to our header. This means we cannot link unless this header does exist. If this header doesn't exist, then the linking will fail. Now we'll need to generate the .bin file out of the .elf file. For that, we have created already a Ninja variable to hold the path and the name of our .bin file. So we expand it here again. This one, to be generated, we need to invoke the object copy rule. The input file will be our elf, and this will be our output. And finally, the most important thing is to provide a default build statement. So this default build statement is the one to be executed whenever we invoke the Ninja command. So whenever we invoke the Ninja command, Ninja basically will parse by default this build.ninja, and it will look for the default target. And our default target will be this .bin. So this will be our entry point to build the whole project. Then it will start expanding the different build statement, then triggering the execution of the different rules, which in return compile the different sources. Now I should be ready to invoke the Ninja command and build the whole project. We start first of all by opening a new Windows command line session on our project top level directory. Then we invoke the Ninja command. If you remember, we have added to the Windows environment variable path the location of our Ninja installation. This means we can invoke the Ninja command from any kind of Windows command line session. Here we go. We have a couple of errors that has been triggered, and my recommendation always is to review the different Ninja build files to spot any kind of errors or typos. I will start by the ARM toolchain one. First of all, the location specified here for my arm-gcc toolchain is wrong. Then I'm missing another character here for the assembler option. If I move to the build.ninja, now the syntax for the invocation of our object copy is wrong. So the input.elf should be located here, and the output should be located in this position. Another syntax issue here is within the linker, so I need to pass this option to the linker. If I don't specify this -wl, then this option will be passed to the compiler, and this map is not recognized by the compiler. Now let's give it another try. Here we go. We are done. So as you can see, the compilation was kind of fast. So Ninja is built to be a fast build tool, at least compared to Make. We have our build directory has been created, and those are the outcome of the compilation and the linking stages. So those are the object files. This is our binary, elf, and map file. As you can see, as side effect of this compilation, we'll have this dependency file created. This will be created by GCC, and whenever we have an update here, then the Ninja will rebuild basically the whole project. Of course, if we invoke Ninja again. This is the log. This is created by Ninja. And finally, we have this depth file created again by Ninja. This one will include the list of the files needed by the different Ninja rules to build our project. Hence, to check which files need to be verified in terms of timestamp to rebuild the project, Ninja first of all will need to read out this file to get the list of the files to be checked, and then it will go over those files one by one in terms of timestamp checking. And if it found out that one of those files, for instance, has an updated timestamp, then it will rebuild the project.